go there, and Thomas was trying to process the particular algorithm, actor critic, deep deterministic policy gradient method. So, and the results are not good, and you have experience working with this method. Let me explain in a couple of words the idea, because it's a paper. Of course, Pavlo and I wrote it, and Jefferson didn't read it. But the idea is that problems with incomplete information can be filtering problems can be solved as POMDPs. And in particular, we proved there that value iteration algorithms converge. So this DDPD, DTPG that Thomas identified is the some of kind of continuous space version of SARSA, which actually maybe Thomas, maybe we'll show a couple of slides, and I'll allow you to share, and show also the algorithm. And there are many issues. One issue, if it's possible to do something that algorithm start to work, but another issue for me, for Pavlo, and maybe Thomas will join us, is to do theoretical results that this corresponding algorithm converge. It's of course has to be. Yes, Pavlo.
Jefferson, look, the idea is very simple. When we have a POMDP, for example, we know the model, but we cannot solve it. To solve this model, we need to reduce it to the completely observable Markov decision process. In this new model, redacted model, you have a state space known, this is a belief probabilities. You have an action space, the old action space. You have new costs or rewards. This is expected rewards by the belief probabilities, but you do not have an access to the transition probability because you cannot compute it. So in this situation, we proposed to use some of the algorithms, something like temporal difference, to find optimal policy because we have a convergence. We obtained the convergence result, or we can justify them. The sum of the algorithms of deep reinforcement learning, where we have state space, action space, rewards, but we do not have exact formulas for transition probabilities. And as we proposed Thomas to realize this model via some algorithms like deep version of SARSA or something like this. And of course, this problem, no, he computed something, but of course, in one day or for a couple of days, to set all parameters to compute the solution that Eugene have in mind. Of course, it is sufficiently hard, but Thomas have a very big progress in this area, And I saw yesterday the version of this, and I was impressed, because in one day to obtain some such results, I think it is very difficult. But today he has
It wasn't one day exactly.
Okay, but I think that Thomas tried to solve exact problem. He tried to solve POMDP, but here we need to compute the solution of COMDP. What's the difference? The difference is that if you compute COMDP, you need to compute belief probabilities where you can use them, and you compute belief probabilities via bias formulas. And in your model, as I yesterday seen, you didn't use this, and therefore I think we have some problems with low range of convergence.
I propose the following, if you don't mind, and Thomas has all the information. Thomas, if you don't mind, first show the last slide we have right now, and I'll explain what's going on. Then, if you could show the algorithm itself, and we'll discuss it, because I also need to understand it better. And then maybe our team will give you some suggestions on what to do. Yes, please show this page 18 that we have now, and I'll explain my. I just sent you the most recent version. You just can take it from what I sent and post it, because this is the latest one.
Like your email from 24 minutes ago. That's the most recent.
Just a second. Let me look at my email. I think I sent it to you. Just a second. Or maybe it's still sitting in drafts. No. No, it doesn't sit in drafts. So sent. Yeah, I just sent it to you. 1047. And just take PDF from it and display.
Yeah, I see that. Should I show the text or just the PDF?
No, just of course PDF.
Okay, I have it up. Yeah.
Okay, page 18, please. And if possible, try to make full screen. Yeah. Yeah. Okay, so what we have here, we have an inventory control problem. It's xt plus 1 equals xt is the state of the inventory, at how much we order, minus dt domain. Okay, and then we have back orders. So this is the equation for the left one for xt. But we don't know xt, we don't know, we know the demand, which is, we don't know the inventory. We know the inventory with noise. And the noise is normal, standard normal Gaussian. And demand is exponential distribution 0.2, which means that on average, they use 5 units of inventory. And there is a holding costs, which are here. So basically, the holding cost is 1 and backordering cost is 5. per unit. Then setup cost 2 is 2. Basically, we have, and unit cost is A, which is very low. So essentially, this is the model without inventory. Without the inventory doesn't cost when you buy something. It's almost free, but it's okay. This is the graph. And could you please move it up a little bit, if it's possible? No, up. You move down. Yes. So basically, he did it for the horizon 4. Now he's trying to do it for big horizon. So my concern is the following. So when we observe, for example, -6, we order close to 40. And when we observe close to 6, we order close to 20. Yeah, so it looks like it has some target area where when it moves it. Yeah, that's basically. Thomas, do you have any comments?
Yeah, I just want to add that like every time like I slightly tweak the results, it kind of comes up with very different policies. So this is just one example I got where, you know, at least it looks like a reasonable policy, and that like it's ordering less when the observation is more. But the main difficulty I've had is like getting it to settle into one policy, because it seems like it's just all over the place everywhere.
Did you succeed with running more iterations?
I'm running something right now, and yeah, you can see like it doesn't make sense at all, this policy that it's ordering. So either it needs more.
How many iterations?
This is 8.
8, yeah.
Yeah, so I think either it needs more training time or the parameters need to be adjusted. I also adjusted like the format of the data to see if that would help. And just, yeah, I haven't gotten it.
Thomas, I have an idiotic question. Idiotic question is the following. In the model, you have parameter D in the formulas that display demand. In the algorithm, you also have parameter D, which is either closer to 1 or to 0. Is it possible that we mix them in the software? It's impossible.
You mean like the demand versus the dimension?
I don't know what does parameter D means in the learning algorithm.
Yeah, because I wanted to make it so it would work for a multi-dimensional problem, but I don't think so.
It's not dimension. It is something. You think it's a dimension? Okay.
Yeah, D is the dimension. Yeah, but no, the demand is as xi in this problem. So there shouldn't be an overlap.
Yes, so it doesn't create a conflict of.
Yeah, there shouldn't be any conflict.
On the indentation, because you have the same parameter. Okay, now Thomas, show us the description of this method, because I don't quite understand it. You send me the link. Yeah, this one exactly. So, guys, do you understand what it is doing? Because first of all,
yeah, I'm still trying to fully understand it myself, but I know like there's 2 classes. There's an actor and a critic, and you have the target network, which is it's continuously trying to update it using the Bellman equation. So it calculates the reward, and then it inches it closer to reward plus gamma times q each time. Yeah, so that's the update each time.
But ideologically, can you show these formulas? Let's try to understand what they mean.
Eugene, maybe we need to look first of all at the classical SARSA algorithm to understand what does this algorithm doing to proceed further to its version of. For this purpose, I propose to open the book of Satan Barto and to look at that to the initial version of the algorithm. And
this is fine, but I just like to mention that I don't think that D is dimensionality. It is something else.
Of course.
Yeah, I do see that there's a D parameter. It looks like it has to do
With exploration, exploitation.
so it's just a special piece of notation, I think. So I'm looking at the spinning up documentation. So D is I guess in their setup they have absorbing states, and D, I guess, yeah, the notation is a little bit confusing, I think, but D is, it just indicates whether, they say it indicates whether the next state is a terminal state or not. I think effectively we can just ignore it.
Yeah, so that stored is done here, so there shouldn't be any conflicts in my code.
Yeah, so I think this is, yeah, in your code it looks like it's D is, like the D in the documentation and D in your code are different.
Yeah.
Okay. Okay, Thomas, can you show the formula again? Because we should be able to understand the meaning of this formula. No, one line above. Is it possible? No. So my understanding that first of all, you said several times that you have x0 equals 0, but if it is the version of Sarsa doesn't have x0.
I changed that based on your suggestion. I made it so it randomly
Yeah, but Sarsa does not have the initial state. It just works with the table. So what about this one? It's not that. No, actually, it has a table. Is phi? I'm sorry. Is phi the policy or phi isn't a policy? Here, phi is a policy.
What is phi? Yeah, phi is a policy. Yeah.
What is phi here?
Yeah, and this one, it definitely seems like a policy because it's Q of phi.
Phi targeting is equal rho phi targeting -1 - rho. This looks like exploration exploitation. So with probability probably with this means.
It's the update rate. So
yes, update. Yeah. Okay. And who decides on rho? The algorithm or you?
I can set it, and I've tried changing it. So in mine, it's called tau. Yeah, it was initially 0.005. I tried making it bigger, and it didn't help. So, and I've also tried changing the learning rate, the expiration noise.
Okay. So Pavlo suggests to switch to Sarsa. Yes, Pavlo?
I mean, if you have some questions about the general idea how this algorithm is working, I propose to open, for example, a book of Satan Barto on its tabular Sarsa version.
Pavlo, let me interrupt you and tell you something. Jefferson just referred, and also I sent it to you, and Thomas was showing there is a manual. that, and it has a link. It is based on some paper by Silver in 2018.
Ah, I see. I mean, okay. If you
Thomas, maybe you opened the paper by Silver. I looked yesterday, but didn't have much time.
Yeah, did you email that to me? Was that one of these ones?
No. This is not what I sent you. It is in the manual. They have reference. You showed the manual. Manual has the reference to Silver. Or maybe I looked at Wikipedia yesterday.
Yeah, it should be at the very
Yeah, at the
bottom.
very end,
Or if
at
you
the very
go,
beginning.
to
Yeah.
the relevant papers. The
Yes,
first.
exactly. This paper by Silver.
I find this algorithm at the Satan Barto book. It's simplified version. If you want, I can share the screen when
Yes,
it
please.
will be appropriate. No, okay. What here? SARSA on policy temporal difference control for estimated the optimal value, Q value, for example. This is one of the version of this algorithm. There is of policy version, etc. But the main idea is the following. Here you no, this is a tabular version. When the space of states and actions are finite, but the continuous version of this algorithm is provided in another place. But to obtain, no, to get the idea, you see this very simple algorithm. Of course, you QSA. This is the estimate. This is частотный estimate.
Frequency, yeah.
Frequency.
But I don't think this is this algorithm. This is
SARS algorithm.
version, but again, they claim that it's not Saturn. They claim that it is Silver.
I understand, but the idea is the same. You you choose A from S using derived from Q as, for example, epsilon greedy, and then taking such. No, the algorithm have two phases. The first is the recalculation of the strategy. The second is recalculation of frequencies for Q. And that's all. And when you have a continuous version, of course, you have also need to make some approximations, and that's all that.
Hello, on this page. Oh, no, don't take it. Show it, please.
Okay.
So where is the policy in this in this page, and where is the frequency? I see only Q function here.
Frequency. This is a frequency.
QSA is frequency.
Yes.
It's not Q function.
So I have a couple comments here. One is I think based on the description in the documentation, I think it's more so I think building from it's more related to Q learning than SARSA. I actually have some slides that I made for my class that kind of show the difference between Q learning and SARSA. So let me. Okay, so I might need to rejoin the meeting. I need to enable sharing. So I'll sign off and I'll sign right back in.
Sarsa, what Sarsa is doing? It's computing key function, or it's not computing key function?
He computing this version that we saw. It's computed the optimal action value function, optimal version. Of course, up to a small parameter. But if you want to compute, for example, optimal policy, you can use, for example, Q-learning of policy temporal control. You can also use expected SARSA to have, for example, some
Jefferson, you can share.
Yeah, so Sarsa and Q-learning are pretty similar. The difference is basically there's pretty much one or two lines that are different. So maybe I should talk through this and then I'll talk through this. So Sarsa is okay. So in both cases you're trying to estimate the Q values, and yeah. So it's like it's been a while since I've looked at these. So okay. So here, so the inputs are you have a step size. You have this is the number of steps in each episode, which is each just like.
Jefferson, can I interrupt you? I'm very, very sorry. So you have policy pi here. Pi is a policy. What is this?
Yeah, so pi is just pi is a policy here.
And what does it mean that when in the next one we take maximum?
Yeah. So thanks. So let me explain what's going on here. So this is the notation I think from Sutton and Barta. So Q star, this is what we usually think of as the optimal value function. So this notation here means that so Q pi is just it's the Q value associated with a particular policy. So here, the Q value associated with a particular policy pi is just so it's the total expected discounted reward you earn when when your initial state is S, you take action S, A, and thereafter you follow the policy pi. So this is just writing out what this Q pi is.
Yeah, and this is true.
So Sarsa works as follows. So we have input parameter is a step size or step size alpha, an episode length t, and an epsilon. This is kind of for doing the epsilon greedy thing in here. So this is again the tabular version. So we start with initial Q value estimates are 0 for all state pairs. And for each episode, so here this just means that you let the MDP run for like 2 steps. So for each time.
Just a second. Let run with what policy? Some initial policy.
So actually here the policy that you're following is it's sort of implicitly defined. So it's implicitly defined based on your current estimate of the Q values. So the policy that you're actually running depends on your estimate of the Q values. So
Jefferson, I'm sorry, may I ask you a question?
Yeah.
Is it required, for example, that the policy visits all the states?
Yeah, I think if you want to prove convergence, yeah, you need, I think, something like that.
Okay.
Epsilon greedy policy means that you, at least with probability epsilon, meet all the states.
No,
all the actions, sorry.
Yeah,
all the action
yeah, so
at the given state, of course.
Right. So yeah, epsilon greedy means that the action so at each time step you have your current estimate of the Q value. Uh,
Mhm.
Initially they're set to 0, but so the first thing you do is you select an action that's epsilon greedy with respect to Q. So I think initially this is just you pick a random action. But in
Or
general,
maybe maximum reward, no?
no, because the one step
Maybe-
reward is folded into the queue.
Mhm.
So in general, though, you have a current set of Q value estimates, and I think I think it's missing from here, but I think you have to sample the initial, you somehow decide what your initial state is.
Mhm.
So for your initial state, you look at the Q value estimate for that initial state. And so epsilon greedy means that with probability 1 minus epsilon, your action that you select maximizes the Q values for that state. You take the maximum overall actions for that state, and then you select an argmax. And then with probability epsilon, you just pick an action uniformly at random.
And sorry, Jefferson, one note. When the maximum attains on more than one point, you take arc maximum randomly over all that points. For example, if all
Yeah.
q's equals 0, you make random action with equal probabilities.
Yeah, yeah. Right. So once you have the action, once you've selected your action, you can see then you get a sample for what the reward is from that action and what the next state is. So in the setup here, the rewards are
Jefferson, I'm very sorry. When you say sample, means that you run reward several times, yeah? What you mean?
so in the setup here, Uh, the one-step rewards are, you think of the one-step rewards as given a state and an action, there's a probability distribution over reward.
Mhm, mhm.
This is realization of
So
that
yeah,
random variable.
so it's
No,
just
my
Realization.
you
question
observe.
is you do it once,
So
realization.
here you do it once, but this is all in the context of you're doing this over multiple episodes as well.
Mhm.
At what?
Uh,
At sorry, Jefferson. At one episode, at epoch T, you make it once. R and S prime.
yeah,
Yes.
yeah. So it's just a single realization here. And then so you select this action and then you get a realization of the reward and the next state. And then the next step is that now you have this next state. So now you select another epsilon greedy action, but now it's with this as your current state.
Mhm.
That's your A prime here.
Mhm.
And then after that, you update your estimate of the Q value for, and so this is note that we're updating here for where the state that you had started in, not this S prime yet. So we update it using this formula here. So it's kind of I think I'm missing a 1 minus. Oh no, that's it's fine. So basically here you have your initial Q, your current Q value estimate for your starting state for that time step and the action that you ended up taking. So you take a step of length alpha towards kind of this is your quote unquote target.
Mhm.
So like the idea I guess is that the optimal Q value should satisfy the optimality equation. And so this, yeah, if this were like so for the true Q values, this should equal this at least an expectation. And here we're just taking a step alpha in, sorry, so that's not it. I guess this is the This is, yeah, the setup here is that this is like your error.
What is this? What is this?
If you look at this part here, so this is the one-step reward, the realization of the one-step reward, and then kind of.
It is at this state or in state S prime. At this
So
state.
this is relative to the state
SA.
action.